In this video, we're going to make a move into what we call analytic trigonometry. This is where we will mix features of algebra with features or concepts in trigonometry. We're going to start with developing some more concepts of trigonometry, and then we're going to start to put those things together so that we can solve equations that involve trigonometric functions, and we'll know all the properties of those functions and how they change when we do these interactions with the algebra. And so this section is going to be about basic identities. And then once we get good with identities, we're going to learn some formulas that we can use that can help us rewrite trigonometric functions or equations that involve trigonometric expressions more simply or more complicated depending on what we want to do mathematically. But this is analytic trigonometry, and I now see that you can't see that word, the full word analytic, the A and the N and then A-L-Y-T-I-C. All right. And so first we're going to review what an identity is for math, right? And so we have two equations here, and I want to know what's the difference between these two equations, right? And so if I were to try to solve this equation to the left, then what I can do, since it is a quadratic equation, is I can expand this. So if I expand that, that's going to be x squared plus 16x plus 64, because this is x plus 8 times x plus 8. And this is going to equal the right-hand side of my equation, right? Well, if I want to solve this quadratic equation, I get everything on one side and 0 on the other. So I subtract x squared from both sides, I subtract 16x from both sides, and I subtract 64 from both sides. And what I'm going to end up with is 0 on each side. And the reason for this is, although these expressions on each side of this equation look different, they are identically the same once we write them in the same manner. So once I multiplied the x plus 8 by x plus 8, I saw that my left-hand side is identically equal to my right-hand side. We call this an identity equation. And identity equations are true for all real numbers where both sides of your equation or both expressions on both sides of your equation are equal or defined. And so since this is a polynomial on each side, we say that the solution is all real numbers. Now, if we come to this equation here, 2x squared plus 7x minus 8 equals 0, if I were to try to solve this equation, it's a quadratic equation. I'm going to take the time to review a concept that we learned in solving quadratic equations. For instance, we can solve by completing the square. I don't want you to ever forget that method. And so I'm going to solve this equation by completing the square. That means I'm going to get my x variables on one side, my constant on the other. I'm going to divide both sides by my leading coefficient, which is 2. So I get set x squared plus 7/2 x equals 4. Remember, we do b over 2 quantity squared, right? Well, that's 7 over 2 quantity squared. All right, 7 over 2 divided by 2, because my b is 7 over 2. I'm sure that it's hard to see that that's 7/2, so I'm going to erase this. But this is 7/2 divided by 2 squared. And when I divide by this 2 here, it's the same thing as multiplying this fraction on the top by 1/2. So that's 7/4 squared, which is 49 over 16. So I add that to both sides of my equation. Now I'm going to have to add it to the 4. I'm just going to write 4 as 64 over 16 so I can have a common denominator with that 16. And then I can factor this, right? It's always going to be that b over 2, the stuff in the parentheses here. So x plus whatever this number is, and that's 7/4 squared, and that's going to be 113 over 16. The reason I write it this way is because I can now take the square root of both sides and solve by extracting the square roots. That's what the method is called. And this is going to be a plus or minus the square root of 113 over 4. I subtract 7/4 from both sides, and I get this equation has these two solutions here. And so since I have these two solutions here, I know that this equation is only true if x equals negative 7/4 plus square root of 113 over 4, or if x equals negative 7/4 minus the square root of 113 over 4. This is not an identity equation. This equation is not always true. It's only true under the condition that x equals one of those values there. And so when we have equations that have at least one solution, and it's not like all real numbers, then we call that type of an equation a conditional equation. All right. So this is an identity equation, and this is a conditional equation. It only is true under the condition that x equals either of those two values. All right. Here, x can equal any real number, right? And so more formally put, two functions f and g are said to be identical if f of x equals g of x, so the left-hand side equals right-hand side, for all values of x where both functions are defined. If an equation is not an identity, then it is a conditional equation, which is what happened here. And so in this section, we're going to focus on what makes trigonometric identities, right? What makes trigonometric identities? And so what we're going to do is we're going to review some of the identities that we actually already know. And so we know that all of our stuff is based off the unit circle, right? We know that sine, if I have an angle alpha, the point where it intersects the unit circle is going to have an x and a y coordinate. Sine of alpha is that x coordinate. Cosine of alpha is that y coordinate. And we can get our other trig functions by doing some variation of x and y. We can do 1 over x. And I wrote that absolutely incorrectly here. Oh, I'm sorry. The sine is the y coordinate. Cosine is the x coordinate, right? We get cosecant by doing 1 over y. We get secant by doing 1 over x. We get tangent by doing y over x. And we get cotangent by doing x over y, right? And so with that stuff being said, we can write our trig functions in terms of our other trig functions in terms of our sine and cosine functions. Now here I used alpha, below they use theta, so I'm going to use theta. So since tangent is y over x, I can write the tangent as sine of theta over cosine of theta, right? These are called quotient identities because they involve the quotient of our sine and cosine functions. I could do a similar thing with cotangent because cotangent is x over y, so that would be cosine of theta divided by sine of theta. These are called our quotient identities. The reciprocal identities are using the reciprocals of our trig functions, right? So since sine is y and cosecant is 1 over y, sine is the same thing as 1 over the cosecant of theta. Cosecant of theta is the same thing as 1 over the sine of theta. They're reciprocals of each other, right? So it's like you flipping the fraction, and flipping is putting one over the other function. Similar for cosine and secant of theta. Since they're reciprocals of each other, cosine of theta equals 1 over secant of theta, and secant of theta equals 1 over cosine of theta. And similarly for tangent and cotangent, tangent is 1 over cotangent of theta, and cotangent is 1 over the tangent of theta. All right, and so these are some of the identities that we already know from just looking at the ratios that we get that are outputs of our regular trig functions. The other identities that we're going to develop in this chapter are new, right? For instance, the Pythagorean identity. These are important identities, some of the most used identities. All right, I have my angle with this terminal side on the initial side on the positive x-axis. I'm going to have an angle theta. This is my angle theta. It intersects my unit circle here. I get an x coordinate and a y coordinate, right? Of course, this creates a right triangle. This side length here is x. This side length here is y. And if I'm in my unit circle, this is 1. Since this is my unit circle, this x and y coordinate are actually your cosine of your angle theta, and your y coordinate is your sine of theta. Now, we know from the Pythagorean identity, a Pythagorean theorem, that when I have a right triangle, if I can square the first leg, add it to the square of the second leg, I'm going to get the square of the hypotenuse, right? Well, since this x is the same thing as cosine of theta, so this is cosine of theta squared plus my y is the sine of theta, sine squared of theta. That's going to equal 1 squared, or 1. Now, we usually don't write it this way when we square a trig function. We write it as sort of superscript on the last letter of the abbreviated trig function's name. So cosine squared of theta, and we read that as sine squared of theta equals 1. And so this is a Pythagorean identity, right? Normally, people write it as sine squared of theta plus cosine squared of theta equals 1. And so you can write it that way, you just switch the order. But from this identity here, we can actually isolate the sine squared of theta, right? For instance, if I subtract cosine squared of theta from both sides here, I'm going to get sine squared of theta on the left hand by itself equals 1 minus cosine squared of theta, right? And so there's a different way that we can write this, right? So if we ever see a 1 minus cosine squared, we can replace that with sine squared, okay? And we can do the same thing, but by isolating this cosine squared, right? If I isolate the cosine squared, that means I subtract sine squared from both sides. So my left-hand side is only going to have cosine squared, and that's going to equal 1 minus sine squared theta. This is another way that we can write our Pythagorean identity, all right? Now, from this identity, all right, I'm going to write it as sine squared of theta plus cosine squared of theta equals 1. What we can do is we can divide both sides by cosine squared of theta, for instance, right? So I'll take my sine squared of theta plus cosine squared of theta equals 1, and I'm going to divide this side by cosine squared of theta, and I'm going to divide both this side by cosine squared of theta. This is valid as long as cosine squared of theta does not equal 1. All right, I mean equals 0 because we'd be dividing by 0. But notice here I have one single denominator, so each of these separately get divided by cosine squared. Well, when I do sine squared over cosine squared, they're both squared. We know from before, from our quotient identity, that sine over cosine is tangent. Well, if I have sine squared over cosine squared, I'm going to have a tangent squared of theta. Okay, so that's dividing it here. I also have to divide it here, right? One single denominator, you divide both things by that denominator. So I have a cosine squared divided by cosine squared, which is 1. And then over here, I have 1 over the cosine squared of theta. This brings up a reciprocal identity. If I go back up, 1 divided by cosine is the exact same thing as secant. And so since it's squared, it's going to be a secant squared of theta. All right. So this is another Pythagorean identity, that tangent squared plus 1 equals secant squared of theta. All right. And then I can do a similar thing by dividing both sides of this original one by sine squared of theta. All right. I'm going to show a little less work here. When I divide sine squared divided by sine squared, I'm going to get a 1. Cosine squared, if I divide that by sine squared, I'm going to get a cotangent squared of theta. And then a 1 divided by sine squared is going to give me a cosecant squared of theta. And so this is another trig identity. Now, this has our cosecant function isolated, our cosecant squared function isolated. If I wanted to isolate the cotangent function, all I have to do is subtract 1 from both sides of this equation. A similar thing here. This has the secant squared function isolated on one side by itself. If I wanted the tangent function isolated on one side by itself, I can subtract 1 from both sides. All right, and so we'll have different ways that we can write each of our trig functions in terms of the square of another one, right? And there we go. And so these are the most important identities, some of the most important and the basic identities that you have to know and memorize. You have to know these, you have to memorize these. Because what we want to do is we want to be able to see these trigonometric functions and these identities so that we can rewrite expressions so that they look similar. Because when we get to other math, sometimes working with an expression that looks very complicated can be much more simplified if we use trig identities to simplify them or rewrite them. And so trigonometric identities allow us to do the following. Number 1, write trig functions in terms of other trig functions, right? So if I don't want to work with a tangent, or I don't want to work with a secant or a cosecant or a cotangent, then I can write everything in terms of sine and cosine, right? So that's one thing that we could do. We can simplify trig expressions written with more than one trig function, right? Hopefully some things can cancel when we write them all in different ways. And then we can evaluate other trig functions when the value of one trig function is known. That is the goal of what we're going to do today. And we're going to start with this first example here, or the second example. We can simplify the expression 1 plus the cosine of beta times the quantity 1 minus cotangent beta sine beta. Now with this, our angle here is beta. Notice that each of those trig functions are evaluated at the same angle, beta. When I do that, when I have that case, I can rewrite all of my trig functions in a good way. All right, not a good way, but I can apply my identities. My identities always assume that we have the exact same variable in these, right? All of these are thetas. All of these are thetas, right? Every identity uses the same angles, right? And so you got to be careful to be sure that you have that. But what I want to do is I want to simplify this expression. This means I don't want to see as many trig functions, and maybe I want to get this as simple as just one trig function, or a fraction involving trig functions or something, right? And I don't want it to be more complicated. I wanted to simplify it until I can't see any more trig identities. And so here, this is what we're going to do. All right, now I see a 1 plus a cosine of beta times a 1 minus cotangent beta times sine of beta. I don't see any of those identities blatantly sitting there. What I do see is that I have a cotangent, and whereas each of these are written in terms of sine and cosine. And so my first bet is to try to write that cotangent as a cosine of beta over a sine of beta and see if some things happen. Now, I rewrote my cotangent of beta as cosine over sine, and it's still multiplied by that sine there, but this sine is like being over 1. And so what happens here is that I can cancel the sine of betas by algebra, and I get a 1 minus cosine of beta here. All right, now I notice some other things. Now, the thing that I'm noticing here is not from trigonometry. The thing I'm noticing here is from algebra. This is like the a plus b times a minus b from algebra, right? That's a difference of squares. That's how you factor a difference of squares. And so if I wanted to simplify this so that I don't have all of this multiplication here, then what I can do is use this formula or use my FOIL method. 1 times 1 is 1. 1 times a negative cosine of beta is a negative cosine of beta. But it's going to cancel with this term when I multiply by that 1 times a cosine of beta, right? And then this last term is going to give me a minus cosine squared of beta. Okay, and so I get this expression here. Now I have a trig function squared. The only identities that involve trig function squared are your Pythagorean identities. And notice here, I have a 1 minus cosine squared of beta. Well, I know cosine squared plus sine squared equals 1. And if I subtracted cosine squared from both sides, I get that 1 minus cosine squared, which is, sorry, if I subtract the sine squared from both sides, I get cosine squared equals 1 minus sine squared. But if I subtract the cosine squared, that would be sine squared equals 1 minus cosine squared. And so that's the form that I have there. And so this is going to equal a sine squared of beta. And this is as simple as I can go. And notice this is a lot less complicated than this right here. And so if I can see a calculus problem, me giving you this calculus problem and telling you, find something. There's something called the derivative. Find the derivative of this function here. The derivative of this is much more complicated if I leave this written in this form here. However, if I change it and write it in this form, it's much more simple for me to figure that out. And so knowing this stuff is going to be applicable, if not in real life, it's going to be applicable in calculus next semester. All right, let's do another example where we use identities to find the exact values of alpha for the remaining trig functions if, that should be an S on that trig functions, if sine of alpha equals 3/4 and pi over 2 is less than alpha is less than pi. Our angle alpha is between pi over 2 and pi. What does this mean, right? Well, if I think about my unit circle, pi over 2 and pi means I'm in the second quadrant. The terminal side of my angle is in the second quadrant. I don't know my actual value. In fact, it is not one of my known angles on my unit circle because the sine is 3/4. It's going to either be 33/2, 1/2, square root of 2/2, 1, -1, or 0, right? So since that is not one of those, this angle alpha is not one of my trig functions. But I can use my identities and the fact that sine of that angle equals 3/4 to find the cosine of that angle, the tangent, cotangent, secant, and cosecant. All right. And so first what I'm going to do is, well, since I know that the sine is 3/4, first I'm going to find the cosecant of that angle alpha, right? Cosecant of alpha. Because I know cosecant of alpha equals 1 over the sine of alpha. That's our Pythagorean identity, our reciprocal identity. And so since the sine is 3/4, I do 1 over 3/4, which is the same thing as doing the reciprocal, which is 4/3. And so I know that the cosecant of that angle is 4/3. Since I know the sine, I can also find the cosine of that angle by using my, all right, I'm just going to go to the basic Pythagorean identity. All right. Now, I know my sine here, right, is 3/4. All right, so since that says sine squared, I'm going to do 3/4 squared plus cosine squared of alpha equals 1. Well, 3/4 squared is 9/16. And now I'm going to solve this equation for cosine squared. I'm going to subtract 9/16 from both sides. I get 7/16. I can take the square root of both sides, and I get cosine of alpha. Remember, we take the square root, we put it on the plus or minus. That's going to be the square root of 7, and the square root of 16 is 4, right? Now, it's only going to be one of these answers here, right? Because and the way we figure out which one it's going to be, right, is to look at this placement of this angle. This is why we say the angle is between pi over 2 and pi. That means it's in the second quadrant. Well, in the second quadrant, our cosine function is negative, so it has to be negative square root of 7/4. So notice I was given my sine, I got my cosecant, and I have my cosine. Now I can find my other trig functions. For instance, I can find my secant function, because secant and cosine are reciprocals, right? And so since I just found that my cosine was negative square root of 7/4, so my secant will be 1 over that. Well, 1 over that is to do the reciprocal. And so that I know now that my secant of alpha is going to be negative 4 square root of 7/7. I'm going to rationalize that denominator. And so I have that one. Next is I can find my tangent. Well, we know that tangent of alpha, all right, the tangent equals the sine of alpha over the cosine of alpha. You can use a Pythagorean identity that tangent squared plus 1 equals secant squared. But this one is a little simpler to me because I don't have to worry about squaring anything. And so since my sine was 3/4 and my cosine was negative square root of 7/4, I know that this is the same as multiplying by the reciprocal of that denominator. 4 is canceled, and so I get negative 3 over the square root of 7. I can rationalize my denominator, and I'm going to get tangent of alpha equals negative 3 square root of 7/7. All right, so I have my tangent. Now, I can do multiple things. I can find my cotangent the exact same way, or I can say that, oh, well, since I know my tangent, it's just 1 over the tangent of that angle alpha. Now, this is the rationalized version. I'm going to go to this unrationalized version here, right? My tangent, that's still my tangent, negative 3 over the square root of 7. This has a lot of extra fluff, right, because I simplified it. But when I do the reciprocal of this, it's just going to be negative square root of 7/3. And so that's why I went to that version. You can always go back to flipping this, right? So it's equal to the 1 over this tangent here when it's written in this form. So, but that'll be negative 7/3 square root of 7. And when I rationalize that denominator, it'll be a negative 7 square root of 7 over 3 times 7, or 21. And those 7s cancel. So you have to do that other simplification, and you get negative square root of 7/3. All right, which is the same thing I did when I went to this step right here. All right. But I know the other 5 trig functions by using the fact that I'm given one of my trig functions and I know what quadrant that angle lies in. This is a very important problem. You're going to see this again several times on graded assignments. I just want you to know that. All right. All right. Now we're going to get to some other identities, right? We're going to talk about even and odd functions. For instance, we know that for a function to be even, when we plug in negative x, we're going to get the same thing as if we plug in a positive x, right? And the reason for this, even functions have symmetry with respect to the y-axis. And so one of the most widely known even functions, y equals the square root of, y equals x squared. Oh, this graph is bad. Let's not put the xy plane there. But negative x would be here, positive x would be here. They have the same y values, right? And so that's why this works. That should be an S. And then if a function is odd, then you get the opposite of f of x, okay? And this has symmetry with respect to the origin. And when something has symmetry with respect to the origin, it's like reflecting part of that graph that's in the first quadrant. For instance, if I look at f of x equals x cubed, all right, this is not the best graph, but you get the picture of where I'm going here. If you reflect this part across the x-axis and then reflect it across the y-axis, you're going to get to this part that's in the third quadrant. All right. Or you can think about it rotating things 180 degrees and you'll get to the same graph that you had. All right. And so looking at our trig functions, you can look at this. You can tell that this goes through the origin. It goes up to 1, 0, -1, 0. When I go from 0 to 2 pi, this is y equals sine of x. This function is actually odd. When I plug in pi over 2, I get 1. If I plug in negative pi over 2, I'm going to get -1. When I plug in pi, I get 0. The opposite of pi, opposite of 0 is -0. I mean, which is 0, right? Plug in 3 pi over 2, I get -1. If I plug in -3 pi over 2, you don't see it on this graph, but you can see that this is going up to +1, right? So when I plug in the negative, I get the opposite of what I get when I plug in the positive, right? So y equals sine of x is odd. If sine of x is odd, its reciprocal is also odd. So cosecant of x is also odd. All right, the cosine function, right, goes from 1, 0, -1, 0, 1. If you just look at this part, you can already see that it's symmetric with respect to the y-axis. And so y equals cosine of x is odd and, even. And its reciprocal secant of x is also even. And then with the tangent function, its reciprocal, they're both odd. Notice when I plug in negative power 4, I get -1. If I plug in positive power 4, I'm going to get a +1, so on and so forth, right? Now, there's value in this, right? What we were doing when we were evaluating trig functions, so for instance, say I gave you the sine of negative 2 pi over 3, right? We'd say, oh, well, you can figure this out by, okay, well, since 2 pi over 3 is a positive 2 pi over 3 would be over here in the second quadrant, then I know that negative 2 pi over 3 would be in the third quadrant. And so this would be a negative value, and the reference angle is sine of is pi over 3. And we know that the sine of pi over 3 is square root of 3 over 2. And so this would be a negative square root of 3 over 2, right? Well, when we do this, when we know the even and odd identities, we no longer have to worry about this negative sign, right? We can use the fact that this function is odd and only focus on positive angles. For instance, I know that since my sine function is odd, this sine of negative pi over 3 is the opposite of sine of positive 2 pi over 3, right? And so it's going to be negative, and then the sine of 2 pi over 3 is actually positive because it is in the second quadrant, and it's going to be a square root of 3 over 2, right? So any negative angle, right, cosine of negative 150 degrees, since it is even, is the same thing as the cosine of 150 degrees. Tangent of negative pi over 4 is the same thing as negative tangent of pi over 4 because tangent is an odd function. And so when you plug in a negative, you get the opposite of what you get when you plug in the positive function. And so you can use this to help you evaluate trig functions. Sometimes it makes it easier, but the choice is yours. In addition to using it to evaluate trig functions, we can also determine if a graph of a trig function is even or odd in case we want to graph it, right? And so this is the product of sine and cosine multiplied by 2. If I want to see if it's even, odd, or neither, then what I'm going to do is what we did before. We replace our x's with negative x's. All right. Now, when I do this, I know that my sine function is odd, right? So this is the same thing as negative sine of x. Cosine function is even, so this is just the same thing as cosine of positive x, right? So I have a positive 2 times a negative times another positive. Well, that's going to be a negative. I can bring that out front, and it's 2 sine of x cosine of x. And this is the opposite. This is the negative of what I started with, which is negative f of x. So when I start with f of negative x and I end up with the opposite of it, I know that my function is odd. That's all for this video. We'll see you during the next video.